alkynes are made from, well, alkynes. The way you make alkynes is simply by taking a smaller alkyne and making it into a bigger alkyne. Simplest of all alkynes is acetylene. Think about acetylene, or any terminal alkyne, is that this proton is unusually acidic for a carbon group. Its pKa is roughly around 25. In order to remove that proton, you need to treat it with a pretty strong base, such as NaNH2. And the product you get then is what's referred to as an acetylide. And ammonia. Ammonia has a pKa roughly around 35 or so, so it's a pretty much an irreversible deprotonation to give you this. And this is a strong base and an SN2 nucleophile. Since this is an SN2 nucleophile, you can use it in SN2 reactions. However, since it's a strong base, you have to use unhindered electrophiles. So typically, primary carbons, methyl groups, or groups where E2 is not a possibility. So, on this, if you want to add a methyl group, you can add CH3I to this sodium acetylide. And you get this. The mechanism is simply anion, iodomethane, 2 arrows. Step is not reversible. And this gives you another alkyne. This alkyne is what's referred to as a terminal alkyne, or at the end of a chain. Terminal alkynes are recognizable by they have a CH proton. Of course, you can remove that CH proton with, again, sodium amide. And then you can react this with another SN2 electrophile, like bromopropane, to give you the product. This is not a terminal alkyne. You can't add any more carbon units to this because it no longer has any acidic hydrogens you can pull off and make into a good nucleophile. Working backwards, say you were given a bigger alkyne. And you had to work your way backwards. What you do is you make the bond next to the triple bond. Here we have two choices, A and B, to make this molecule. Choice A. Means the leaving group goes on the sp3 carbon and the sodium goes on the acetylide. Choice B. Sodium goes again on the sp carbon, and the leaving group goes on the sp3 carbon. Which choice is better? Well, this does SN2 and E2. This does them all, SN2, E1, E2, and SN1. SN2, E2, SN2, E2, tie goes to E2. So this does not really give this as the major product. Instead, it gives you E2 as a major pathway, and not the product that you want. This, on the other hand, can do SN2 and E2. This can do SN2. We have agreement. SN2 is going to be the major pathway. So you always want to cut the bond next to the least substituted carbon. Other thing, this example right here. You want to cut the bond right here. Not only is this carbon less substituted, carbon A, but carbon B is an sp2 carbon, so you can't do the SN2 reaction. So the way this methodology works is simply an SN2 reaction. And since it's an SN2 reaction, you have to follow all the rules of the SN2 reaction, which mainly are: you need a good nucleophile, which the sodium acetylides are. You need to have a good leaving group. Suggest you use a Br or a tosylate as your leaving group. And it needs to be an unhindered carbon. So primary or methyl.